Okay, you guys have done some stuff with natural logs in the past, right? Let's take a second. Question?
So is this our like last chapter?
Yeah, the last little section we'll cover. Yeah, this, and I'm not gonna do, I'm not gonna do a ton with it, but I want you to, something I think you need to see. The last thing I feel like I want you to see. After this, we can just ease into summer a little bit. So think about natural log. Think about what you know about the natural log function. Let's go back to pre-calculus. What is the graph? Remember what the graph of a natural log function looks like?
No.
Not at all. Okay, well, that's probably worth looking at. Yeah, natural log. Maybe before we even do that, let's look at some properties. I know you'll remember that stuff, right? So properties of logs. If we talk about let's just talk about a general non-specific log. If we said something like the base A log of B equals X. So what's another, you might remember a couple things, and I think this will be a lot clearer when we're done talking about it because it gives you a little background into why these things are the case. But you can always make a corresponding exponential statement. Okay. Say it again? Yeah, right. And the way you can always remember that, just remember the simple statement, a log is an exponent, right? So a log is always equal to the exponent, right? So this is the same thing as saying B equals A to the X, right? Now we've got some properties of logs that are very useful to us, and we make liberal use of them in calculus. Hey, Jeremy, why don't you go ahead and close that up and have a look here. This is you're going to want to see this. Go ahead. So we got some properties of this. Just to simplify things, we're going to focus on what is a natural log, by the way? Okay, base E, right? So if we want to talk about a natural log, natural log is just a base E log of something, right? So the base E log of X, we would say, we write it as natural log of X. And you don't say that, just so you know, you don't say ln, you say natural log. You say ln in college, people are going to laugh at you. So it's the natural log of X is how you say that. I know they write it ln, and that's French for logarithm naturel or something crazy like that, but it means natural logarithms, okay? So what are some properties of natural logs then? Of all logs, but we'll focus on natural logs because they're easier to write, for one thing. I want you to recognize a pattern here. So if we have the natural log of X to the A, let's figure out what that equals, and let's compare that to the natural log of a product and the natural log of a quotient. Yeah, there we go. Okay, so what do our properties tell us about these things? Do you remember how we can simplify the natural log of an exponential? No. What is it? No, there's an easier way to do this. It's a very simple property. If I have a log of a base to a power, I can always pull the exponent out front, right? So we can write this as A times the log of X for any base. It doesn't have to be a natural log, but like I say, natural logs are easier to write, so we'll just use those. I'm lazy. Okay, what about this one? What's the log of a product? Yeah, okay, it's the sum of the logs. And the log of a quotient? Okay, good. So think what that just did. If you think about the sort of the hierarchy of complexity of arithmetic relationships. So we've got think about this in terms of like things you do with order of operations. Wouldn't you say that the easiest stuff to do arithmetically is add and subtract? That's like the lowest rung on the ladder, right? Step one rung up the ladder and you get to products and quotients. Step one rung up from that and you get to exponentials, right? Does that make sense? So when you apply these properties of logs, you're essentially stepping one rung down the ladder. You're making things simpler, right? You're moving from an exponential relationship to a product relationship, right? You're moving from a product relationship to a sum, that's easy, and from a quotient to a difference, right? So we'll come back to this soon, and we're going to take advantage of this because can you already kind of anticipate that if you had something, like let's say you had a really complicated relationship, arithmetic relationship between two expressions, like in an equation, for example, right? If you were to take the log of both sides of that equation, sure, you're introducing another function, but it can serve the purpose of taking all those complicated relationships and making them one step simpler, right? And that's going to lead us into a technique called logarithmic differentiation that we actually use when we're solving complicated differential equations, okay? So we got these properties of logs. Let's take a look and remind ourselves, and we'll do a little practice with these too. I'll come back to this stuff. Let's look at what the graph of a natural log function looks like. Okay, so remember that it crosses the x-axis where? At what x value? At 1. There you go. So it crosses at 1. So that's telling us one thing. That's telling us that the natural log of 1 equals 0. Okay, that's important. What does it look like? Where is it defined? For what values of x can we take a natural log? All positive values, right. It's only defined for positive values of x. Good job. Okay, so we know that log x, the domain of log x, the domain is x has to be greater than 0, right? Do you remember what this curve looks like?
No.
Do you remember what an exponential graph looks like? Y equals e to the x. What's that look like? Okay, that one we know. It goes like this, doesn't it? Right, if I were to graph the function, yeah, I didn't really think ahead here. Let me just change one little thing. I'll draw that again, but I want to be able to go. Here's a way I think I can cement this in your brain so you won't forget it. So this is a log function. We know it goes through that point. Exponential, you know though. Exponential, you told me it does this kind of a thing, right? So it's asymptotic on the negative x-axis. Everybody agree? Right? And then it's going to go through the y-axis, and then it's just going to increase exponentially, right? What point does it go through on the y-axis? 1. It goes through 0, 1, doesn't it? Right? Whoops. Right? And it's going to go like that. I missed the point, but you get the idea, right? Goes through the point 1. So that's the graph of the function, call it g of x, equals e to the x. Right? Remember this stuff?
No.
Vaguely?
No.
Okay. If you write it as, well, if I put an a there, a is just the initial value, the value at 0, right? And this tells us that e to the 0 is equal to what? Is equal to 1, isn't it? E to the 0 is equal to 1. And then if I have an a out front, that would multiply the function by a and stretch it up or squish it down, right? But if let's just focus on just the plain old e to the x. If we go back, what's the way I can do this? Yeah, if we go back here, yeah, here we can do it. This will be good. So if we take this statement that you guys told me from the beginning, you immediately remembered this, that base a log of x is equivalent to saying b equals a to the x, right? So if we go back and plug that in here, just grab all this stuff. Yeah, oh, it's doing this again. Oh, I was erasing, wasn't I? Yeah. Okay, so if we apply this to a natural log situation, what's that look like? So if our function is a base E log, right, which is natural log, the base E log, we'll call it x equals y. What does that look like in terms of the corresponding exponential function?
E to the y.
Ah, okay, e to the y equals x, right? Okay, so if we were to if I wanted to solve a log equation, what if I wanted to do this? What if I wanted to say I've got the natural log of 2x equals 4. How could you solve that?
Something to log equals 2x.
Okay, what's the something?
Isn't it 10?
Whatever.
It is
Well, but if it's a natural log, what's the base?
10.
No,
E.
E, right? It's E.
Yeah.
So we've got an E there. So you could, one way to do this, so you guys, you remember this stuff, right? So one way to do this is we could write the corresponding exponential function. We could say 2x equals e to the 4, which is just a number, right? And then divide by 2 and I get my answer.
What's the one that has a 10 normally?
Yeah.
That's a common log, right?
Oh.
Common log. And so if we write, if I write something like the log of 1,000,
It's 10.
It's
10.
10.
it assumes a base 10. So if you write a log with an log log and you don't specify a base, we assume it's a 10. How come? Why is that an important number? Say it again. We have base 10, we use a base 10 counting system, right? So the natural's a bad word. So the common's a bad word too.
Default.
The default, there you go. Nice, there we go. So the default system for us that makes sense, you know, for us when we're doing things like if we want to use, like if you wanted to, I don't want to get into that, but if you wanted to do computations with very large numbers, for example, our numbers are all base 10, and so it used to be back in the, and you still do this sometimes, if you ever see like a log or piece of graph paper, it's, you may not, you will in college, you'll see stuff like that. So log means that on the x-axis, the distance between the vertical axes, the vertical lines, is going to vary. It's going to vary according to a log function. And so every time you step up by one increment, you're stepping up by a power of 10, right, when you do this, by the main increments. And it's like a decibel scale in physics. When you talk about acoustics, you talk about the sound level in decibels. That's a logarithmic scale. And so for us, like it makes sense for us to think about 100 decibels as being, how is that related to 90 decibels? Well, it seems like it's only, it's 10/9 as much, but it's not. Every time you scoot up by small increments on the decibel scale, you're actually moving up by powers of 10, right? And so it's not really the way it works. Like a sound of 60 decibels sounds like it'd be half as loud as 120 decibels, right? No, 60 decibels is barely audible. 120 decibels is real loud, right? That's like a Metallica concert or something, and that's really loud, right? So we see this stuff quite a bit. There's an implied base 10 here. Call that a common log or a base 10 log. What is the answer to that?
10 to
Yeah, it's 3, isn't it? Emily's got this stuff down. So think about it in, what I always do with these is I think of it in terms of a variable, for example. If I were to set this equal to x, and we're trying to solve for x, then this is equivalent to saying 10 to the x equals 1,000. So 10 to what power is 1,000? 3, right? Okay. Okay, there's another way to do this, though. There's another way to do this. We can get to this exponential function in a different way. And this is the way that I don't think you guys talked about very much last year, I have a feeling. And this is a really good way to do it. You can think about logarithms and the corresponding exponential functions as inverses and as undoing each other. Think about how we do things like when we solve equations in math. We can almost do everything we need to do using an order of operations tree. Just think about, just objectively here, kind of philosophically, if you've got a cube function that you need to unlock to solve for a variable, what do you do to both sides of the equation? You cube root it, don't you? How come? Because what?
That's what we were told.
That's what you're told to do, okay. But think about why you're doing that. Let's put this in perspective a little bit here. This is stuff like, this goes back to probably Algebra 2 stuff, but this is a big topic in Algebra 2. Why would you cube root something to get rid of a cube? Because there's a really meaningful,
It just cancels it out.
it cancels it out. Why does it cancel it out?
It's the
It's to
opposite.
1/3.
Okay, because they're opposites, but opposites not the bad word.
It's to the third. They're inverse.
They're inverse functions, right? That's the job of an inverse function. An inverse function is a function that undoes the other function, right? What's it mean? What's the real definition of inverse relations? Won't even exclude ourselves to functions. It's very simple. Inverse relations, a relation is just a mapping, right? A relation is just a rule where I can input an x value, and whatever the rule is, it's going to output a y value. For us, most of the time, it's an equation.
X
Right.
equals Y.
Say it again.
X equals Y.
Right, so when you do an inverse relation, all you're doing is you're flipping the domain and the range, right? So for example, if we take something like, if this is our input rule, this is our relation, if these are x's and y's, let's say our rule is that x maps to 4, 1 maps to 4, 2 maps to 5, 3 maps to 7, okay? That's really simple. We don't know, maybe there's an equation behind the scenes, but we don't know. We just know that's our rule, that's our relation. Then what's the inverse going to be? So if we call this f of x, what's the inverse of f of x going to be? Yeah, I'm just going to flip the domain and the range. I input a 4 and I output a 1. Input a 5 and output a 2. Input a 7 and output a 3, right? Okay, how does that manifest itself in terms of a graph? This is just all Algebra 2 review. This is kind of pertinent review. I think this really helps you get a deeper understanding of what we're going to talk about. So if we were to graph these points, let's graph these points in red. What do they look like? Over 1, up 4, right? Over 2, up 5, over 3, up 7, something like that, okay? If I graph these in blue, I go over 4 and up 1, over 5, up 2, over 7, up 3. What do you notice?
It's over and it's rotating.
They're,
It's the same. It's
So-
reflected over the, it's an opposite.
what line?
The X, Y.
X equals, Y equals X. Yeah, they get reflected over the line. The line of reflection, or the line of symmetry, is the line Y equals X. How come? Because you're interchanging X and Y. You're flipping X and Y, that's all you're doing. So notice that each of these points maps to the other point over that line of reflection when we do an inverse, right? Little hint here too, something else that's really useful, just for when you go to college. If you ever want to come up with a graph of an inverse, it's sort of difficult to reflect over a non-vertical line. Our minds don't do that very well. We're very used to dealing with horizontal and vertical axes because that's how we're trained in math. It's difficult to make this kind of a reflection. There's an alternate way to do it. There's 2 steps you can always do instead of reflecting it. You can take the original function. In this case, it's just the function is just or the relation is just 3 points, but it could be a continuous curve. And you can rotate it counterclockwise 90 degrees and then reflect over the y-axis, and you always get the inverse every time. Like if I took the red ones and did that, what would happen? Well, I would rotate them over to there, right? And then reflect over the y-axis and they end up there, right? What about the blue ones? If I rotate them 90 degrees, let's see, they're gonna end up over here. Then I reflect them over the y-axis and they end up there. Always works, every time. Okay, so the definition of, or the test to determine whether functions are inverses is this. F and G are inverses if and only if f of g of x equals x and g of f of x equals x, right? Okay, that has to be true. So, big deal. Why do I bring all this stuff up? Well, if you look at something like, where's that problem there, Jim? Lost track where we were. Oh, right there. If we look at this one, this problem right here. Okay, there's another way to do this. I could take the same problem and instead of just rewriting it as an exponential, I could undo the log function by taking the inverse of both sides, right? The inverse of a log function. So let's approach this a slightly different way. Let's take the same original function. Okay, and what do you suppose the inverse of a natural log function is? It's the natural exponential function, right? So we can exponentiate both sides. We could take e to the power that's equal to both sides, right? So we're just doing this. E to the base e log of 2x equals e to the 4.
So there's 4 equal.
You just basically move it all up.
You do, right, exactly.
So it's the same thing.
It's the same thing, which brings us to another very important property of logs that we can easily prove. What do you think, what happens? What is e to the base e log of x equal to? Well, let's figure it out. Let's just call it, let's use I'll call it your method, the one that you guys told me immediately to do. If let's set this equal to y and just solve for y, right? Okay, so using your method of coming up with the corresponding exponential function, right? If I've got a base e, right, a log is an exponent, right? So would everybody agree here that this is the same thing as saying e to the y equals e to the x, right? Or let me say it a different way. If we want to come up with what that definition is, right? It might be easier, let me do this the other direction. How about if we did this first? We're going to do both of these, but what if we took the natural log, so the base e log of e to the x? Let's do that one first. I think that's easier, and then we'll jump back to this one. Yeah, right? Everybody agree? Because what does this say? It says a log is an exponent, so the base to the y equals whatever we're taking the log of, right?
Oh, so x equals.
So x equals y, right? That's telling us e to the y equals e to the x, so y equals x, right? So that tells us something important then. The base e log of e to the x equals x. They undo each other. That sounds an awful lot like an inverse, doesn't it? Right? We undid the exponential function by logging it, right? What about up here? Okay, well, isn't this just the reverse of that process, right? If y is equal to e to the log x, then if we flip our thinking around, that's like going from this statement back to this statement, isn't it? Right? Shouldn't I be able to write this as saying then I should already do it in orange, huh? The base e log of x must equal the base e log of y, right? So once again, y equals x. You see that? Right? Because isn't our rule that a log is equal to an exponent? So the natural log of y must equal whatever the exponent is here. You get it? Right? Okay. So either way you slice it, what this tells us two very important things. It tells us that in both cases, we can just replace this y with an x, can't we? Right? So that meets the requirements of an inverse, because e to the log x undoes the log x, it gives us back x, and the natural log of e to the x gives us back x. Those meet the criteria for an inverse, right? So that's an easy way to undo exponential functions, is to log them and vice versa. Okay, this takes us back to our graph though. This all kind of comes together. This is really cool. If these are inverse functions, then what did you guys told me, what's true of the symmetry of their graphs? How are they symmetrical, right? Because here we've got the two functions. We've got the function f of x equal, I guess we call it g of x, didn't we? Call it g of x. Equals e to the x. And then down here, we'll call this f of x equals natural log, the base e log. They've got to have symmetry about the horizontal line through the origin, y equals x. So yeah, now we know what it looks like. It has to look like that, doesn't it? Right? Right?
And then if you rotate that extra degree, what did it do?
Be the same thing. Yeah. Isn't that cool, all that stuff? I just love math. All that stuff comes together. Okay, so then this brings us to our, how does this relate to calculus? Okay, very strongly. Here's how this relates to calculus. The definition, turns out that the actual definition of the natural log function is this. The real definition. The natural log of x is equal to an area function. It's equal to the area under the curve inverse graph, 1 over t dt from 1 to x. Okay, so let's look at a graph of this. Just happen to have something here. We can, what are the odds? Oh, where'd it go?
Only have 5 minutes left, I don't think.
Oh, no, we can do it. Easy. Easy money. So there's our graph of the inverse function 1 over t, right? All we want to do is we want to add up the area under the curve from 1 to x, right? So there's the graph of the function right there. Look at that. What does that look like? There's the function we define. There's our area function, right? The integral of g of t, which is 1 over t from 1 to x. That looks pretty familiar, doesn't it? Right? If we want to add up the area under the graph of this thing, look what we get. Okay, so there's the area under the curve from 1 to 2.2. So this is really the same thing as saying the natural log of 2.2, right? If I turn on this function down here where we just define this new function as L of x, we'll call it L of x equals the natural log of x, notice that it overlaps perfectly with this area function. Agreed, they're the same thing, right? If I turn on this point right here, notice that the output of our area function, right, f of a, so if I choose a to be 2.2, if I calculate the area under the graph of 1 over t from 1 to 2.2, it tells me it's 0.788, blah, 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 right? Well, what do you know? The output of the natural log function, the natural log of a, of 2.2 is 0.788, right? And as I drag a along, you can see that as the area under that curve grows, so does the value of the log function. You can kind of see here, too, why it makes sense that because we're looking at an area under a decreasing curve, the area is growing at a slower and slower rate as we move further to the right, isn't it? So how does that manifest itself in the shape of the natural log graph? It's flatter, right? What's a rate of change of area here? Rate of change of area under the red function is the rate of change of the value of the function. That's a slope, right? A lot of stuff coming together there. Last thing we'll do before we get out of here, let's just try to get a decimal approximation of e, because the definition of e, you already told me that the natural log of e is 1, right? Okay, boy, there's a lot packed into this, huh? So the natural log of e, we want to get our answer, the output, to be about 1, right? So if I scoot this thing down, there's 0.99. Well, we can't get it exactly, but look what we find here. If I input a value of about if I input a value of about 2.7, right, I get out an output value of about 0.9935 something, right? Okay, so that's the value I have to put in to get back an area under the curve of 1, right? So the log of that number is equal to 1. Well, it's somewhere between 2.7 and 2.8. It turns out it's 2.71828, something like that. That's the value of e. That's what we call the natural number. That's like pi. It's a number, it is the number such that the area under the curve from 1 to e is equal to 1, right? Or in other words, the natural log of e equals 1. That's a hugely important number, as we'll see, because that's the base that describes the growth of natural populations, for example. So we can extend this into all kinds of crazy things. We could, just the simple math we talked about here would explain things like the rate of extraction of a finite resource. Like if you want to look at the Gaussian curve that describes the rate at which human beings extract petroleum from the ground, based on this. You take a population of lemmings in Norway and you want to look at the rate of growth, it's based on this. All this stuff comes down, the rate of radioactive decay. It's all this, right? Okay, we'll talk more about it later.